Hello students. In the previous chapter, we discussed about mechanical properties of solids. Mainly, we discussed their elasticity. In this chapter, we will discuss about the mechanical properties of fluids. Here, we will cover both when the fluid is at rest and the fluid is in motion. Mainly, here we are going to discuss hydrostatic pressure, surface tension and viscosity. In this module, I will discuss in detail about hydrostatic pressure. Before starting hydrostatic pressure, we have to recall what is meant by pressure. Pressure is the ratio of thrust to area. What is thrust? Thrust is the total normal force acting on any surface. Here say two types of knives are here. One is sharp knife and other one is dull knife. You know that this sharp knife can cut the vegetables very easily, but the blunt knife it cannot. What is the reason? Because the area of the sharp knife it is less as compared to the dull knife. That means pressure is inversely proportional to area. When we apply same force on both the knives, say that the more effect is on sharp knife. Why? Because the force applied here is passed through a small area. That means the pressure exerted is more here. So we can say that pressure is inversely proportional to area. Pressure is the ratio of thrust to area. Then we call usually thrust is the force. So we will write here pressure is equal to force upon area. But this force is always normal to the surface. So the total normal force is called thrust. You can see that while pinning papers, you must have experienced that it is easier to work with a sharp tip pin than a flatter one. Now you understood what is the reason? Because pressure is inversely proportional to area. So we discussed about what is meant by pressure. Now see, this is a dam. See, the thickness of the wall of the dam increases as we go in deep. What is the reason for this? You have seen the walls of your house, it is having uniform thickness. Then why the walls of the dam is made like this? For understanding that, we have to introduce another physical quantity, that is hydrostatic pressure. What is hydrostatic pressure? The pressure exerted by a fluid at rest is known as hydrostatic pressure. The SI unit of pressure is Newton per meter square or Pascal. So, the pressure unit and hydrostatic pressure unit it will be same only and dimension also will be same. In the previous lesson, we discussed that solids develop shearing stress when deformed by an external force because the magnitude of interatomic forces is very large. But fluids do not have shearing stress, and when an object is submerged in a fluid, the force due to the fluid acts normal to the surface of the object. Also, the fluid exerts a force on the container normal to its walls and at all the points. The normal force or thrust per unit area exerted by a fluid is called pressure. We denoted by P, and P is equal to thrust upon area. Here see, this cube is immersed in a fluid. Then say from all sides this liquid is exerting force on the walls of this cube, but this force is always normal to the surface of the cube. So we call this force as thrust. So we can say that pressure is equal to thrust upon area. The same way the walls of this container, here also the force exerted by the fluid is normal to the walls. Here we are going to derive the expression for hydrostatic pressure at a point inside a liquid or a gauge pressure. For that we will consider this diagram. Consider a liquid in a container and an imaginary right circular cylinder of cross-sectional area A and a height h. Let the pressure exerted by the liquid on the bottom wall, it is P1, and the top wall, it is P2. Therefore, the upward force exerted by the fluid on this area, that is P1A, and the downward force exerted by the fluid on this area, that is P2A, downward. So, the total force exerted due to pressure, that is P1A minus P2A, that is in the upward direction. The weight of the cylinder, that is acting downwards. We will see how much is the weight of the cylinder. The weight of the cylinder, that is equal to mass of the cylinder into acceleration due to gravity. Mass of the cylinder means volume of the cylinder into density of this liquid. We will take the density of this liquid is rho. Then what is the volume of the cylinder? Volume of the cylinder is equal to A into H, that is area of the face into height, that is A into H. That means the total mass is equal to A into H into rho. Then the weight of the liquid acting downwards, that is AH rho G. That is equal to the upward force. That means the downward force AH rho G is equal to the upward force P1 minus P2 into A. Then only the cylinder will be in equilibrium. So when the cylinder is in equilibrium, we can say that P1 minus P2 into A is equal to AH rho G. Then A will be cancelled on both sides. Finally, you will get P1 minus P2, that is equal to H rho G. We will see the derivation whatever it is given here. See this, whatever I explained there, it is given here. Consider a liquid in a container and an imaginary right circular cylinder of cross-sectional area and a height h as shown in the figure. That figure you have to refer. Then the pressure exerted by the liquid on the bottom and top of the cylinder be P1 and P2 respectively. Therefore, the upward force exerted by the liquid on the bottom of the cylinder is P1A, that I told you, and the downward force it is P2A. So the net force in the upward direction is P1A minus P2A. Then mass of the cylinder, that is density into volume of the cylinder. Rho is the density of the liquid. So weight of the liquid in the cylinder, that is equal to rho G H into A. Since the cylinder is in equilibrium, the resultant force acting or it must be equal to 0. That is, we have seen that P1A minus P2A minus rho G H A is equal to 0. That is P1 minus P2 is equal to rho G H. That means we can say that P1 minus P2 is equal to rho G H. It is called gauge pressure. Consider this cylinder, the top surface is on the liquid surface. That means it is exposed to atmosphere. That means the pressure P2 is nearly equal to P atmosphere. The pressure P2 is nearly equal to P atmosphere. And the pressure at the bottom side, that P1, that we will take it as P. Now we can replace the previous equation to P minus P atmosphere is equal to rho g h. That is, P is equal to P atmosphere plus rho g h. Suppose we want to find out the pressure at a depth, we have to calculate how much is the pressure exerted by the atmosphere till the surface plus the pressure exerted by the liquid. That is why the pressure at a depth P is equal to P atmosphere plus H rho g. Anyway, we have seen that the pressure difference or pressure at a depth is directly proportional to depth, that H. This is the reason we have already discussed when we go too deep, the walls of the dam become thicker. This is the answer for that. Why? Because the pressure is directly proportional to depth H. For sustaining this pressure, the wall of the dam made thick at the bottom. We have seen that the pressure at a point is directly proportional to depth. That is, P is proportional to H. P minus P atmosphere is proportional to H. That means it is independent of the area of the cylinder. It means that pressure in a liquid at a given depth is equal irrespective of the shape of the vessel. Here you can say that different shape of vessels are here, but the pressure at the same depth it is same, because the pressure is independent of the area, it depends only on the height. This property, this phenomena, it is called a hydrostatic paradox. Hydrostatic paradox, it is showing that we have taken the liquid in different shape vessels, but it is independent of the shape of the vessel and it depends only on the depth, that is the height.